So today we are going over two different types of finance problems, two different formulas that we can use to help us compound interest. Now you might be wondering, why the heck are we doing this in this unit? Well, these two formulas are actually exponential formulas. So these are basically the word problems, the real world applications for exponentials. And this is our unit over exponentials and logs. That's why we're going over it. Now, like I said, there are two different formulas we're going to learn. The first is just compound interest, which I should mention that these finance concepts, this is not the first time you've seen this. You also went over these two formulas in Algebra 2. So this is not brand new to you. Hopefully some of it seems familiar. It's not too tricky. As long as you know how to find the variables and you know the formula, you should be all set. So like I said, the first thing we're going to go over is compound interest, and it says here, a common application of exponential growth is compound interest. Compound interest is the interest paid on both the initial investment, called the principal, and on previously earned interest. Now, compound interest can be compounded a different times per year. It could be compounded monthly, daily, bi-weekly, weekly, annually. These are all different types of time periods that we could have for compound interest. Now, first, I'm going to write down our formula, and then we're going to define each one of the variables in the formula. So, our formula for compound interest is A equals P times 1 plus R over N raised to the power N times T. Where A is the total amount in your account. That's why it's a big A. We don't want to make it a big T because that can be associated with time, and we don't really want that associated with time. So we make it a big A. Then P stands for principal. And remember, principal is like the initial investment. The initial amount that you put into your account. The R stands for the interest rate. It's the rate that you're accumulating interest. Now, when we're putting the rate into our formula, we always put it in as a decimal. Not as a percentage, which is how they'll give it to us. We need to convert it into a decimal. The N stands for the number of times you're compounding per year. And when I say compounded, it just means like calculated, really. So it's the number of times you're calculating the interest per year. Just in finance, instead of saying calculated, they say compounded when dealing with interest. And T does, of course, stand for time. This is how long you've had the account for. In years, I should say. All right. So let's take this formula and try it. Number 1 says Dave invests $300 in an account with 5% interest rate. If he makes no other deposits or withdrawals, find his account balance after 15 years if the interest is compounded with the following frequencies. So we're having to solve this problem twice. Once for if we're compounding semi-annually, and the other for when we're compounding monthly. We use the exact same formula each time because we're compounding a certain amount per year. What is our principal in this problem? Yeah, it's that $300 amount that Dave invests. That's what we put as our principal, our initial amount. Then we have 1 plus. Now, what is our rate? %. Now, we're not going to put 5 in for our rate. We need to convert it into a decimal. How do we do this? Yes, exactly. You either think of it as moving the decimal 2 places to the left, or, like Peyton said, you divide by 100. So our rate, is actually 0.05. And if we are compounding semi-annually, what does this mean our N is? We're compounding semi-annually. What does this mean? So, not quite. Annually means year. If you say something is annual, it means it's yearly. If you say semi-annually, remember, semi means half. You're compounding every half year. Or, yes, Sydney, twice a year. N is 2. Semi-annually, like if you have an event that occurs semi-annually, it means it occurs twice a year. So our N is 2. I input 2 for N. And then my last step is to insert my time. How long is the account open for? Or when do I want to know my total amount? After how many years? 15 years, yes, that's my T. So I plug in 15 for T, and then my last step is just to plug all of this into my calculator. And you get $629.27. After 15 years, Dave has basically doubled his money. If we're compounding semi-annually. So now, it wants us to use the same word problem, but instead compound monthly. So what's the only thing that's changing here? N, yes. What is N now? What is N now? 12. Monthly means we're compounding. For every month of the year, there are 12 months in the year. And everything else remains the same. I have an initial investment of 300. I have a rate of 0.05. My 2 in the original problem is now substituted in for a 12. And my time is still 15. So let's see. 300. Well, what I can do is I can just do this, can't I? Okay. And we have 634.11. In 15 years, we have accumulated $634.11. Looking at these two amounts, what do you think this means? What can you conclude based on seeing these two amounts? 629 and 634. What's better? The monthly. The monthly. Yes, Dawson, that's what I'm looking for. The more times you compound per year, the better off you are when you are earning interest on an account. So if we had even bumped this up to bi-monthly or even daily, it would have been an even better investment. The more times you compound per year, the more money you'll earn. All right, so let's do another one. Let's see, do I want to do number 2? I'm not going to do number 2, but we are going to talk about how to find the N, the number of times compounded for each one of these. If we're compounding quarterly, what is my N here? Yes, quarterly means 4 times a year. So N is 4. What about daily? What's my N value here if I'm compounding daily? $365, yes. And I'm not actually going to solve, well, I guess I could show you how to write the equation just because I want to show you the difference between these two amounts that we get if we're compounding quarterly versus daily. So here in this first one, we have an investment of $2,500. Our rate is 8%, so we put 0.08 over N, which is 4. And then it is after 25 years. So if I plug that all in my calculator, I actually get 1111.62 dollars. Versus if I do it daily, it's all of the same amounts. The only difference is my N is now 365. So if I plug all that in my calculator, I actually end up with $18,468.59. So you can see it's more than $300 in added interest that you get when you go from quarterly to daily. Also, the reverse holds true. So if you're taking out a loan, which is money owed, and the bank says, oh, we're going to compound this daily, that means you're going to owe more money in the end than if it had been compounded monthly. Which, just so you know, like banks will always compound, I don't know if it's daily or even continuously, I forget. Because they always want more money, right? They always want more money from you. All right, so let's do this word problem. Do I want to do this word problem? No. Let's skip to number 4. Let's skip to number 4. So it says, suppose a savings account offers a 0.4% interest rate compounded semi-annually. If Samantha opens an account with $750 and makes no other deposits or withdrawals, how much interest will she have earned after 10 years? So I start off my formula as A equals. What is my principal? What is my p-value here? Yes, 750 is P. 1 plus, what do I put down as my rate? What is my rate? Yes, you take that decimal and you move it 2 to the left, you end up with 0.004. Now, what's my n in this case? What's my n? Yes, semi-annually, remember, semi means half, annually means year, so semi-annually is actually 2 times per year. And what is my time? 10 years. So I'm going to plug that all in. And I should move on. I'm done. Am I done? Should I enter this in Math Excel and move on? Lauren says no. Why? Why should I not just move on and be done? This is my amount, right? What's wrong? What do I need to do further here? What is it actually asking for in that last sentence? Yes, guys, you do need to subtract. Yes, all it wants is to know how much interest she's earned. So to know the amount of interest she's earned off of her initial investment, what you actually have to do is take her amount that she's earned and subtract how much she initially invested. So in 10 years, she has earned, now that's awful. This is not a very good account. But she has earned $30.58. Making sure that with money, we're always rounding to the hundredths place. Sometimes they like to be tricky like that. You think that you've solved for what you need to solve for, but then in the end, they're asking for something different. So just make sure that you're answering the question. All right, now I'm not going to solve the next one, but I do want to discuss. To find the rate when it's given as, now this is a mixed number, all you have to do is put the fraction in. So this is actually 2.375. Then to get your rate, remember it's the same. We move the decimal 2 places over. So our rate is actually 0.02375 in this case. Also, the time for this problem, we start in 1990, and we're going to 2025. So our time is just the amount of years between those 2 years, 35. All right, so now there's one other type. So all of these have been the same type of compounded interest, right? We're using the same formula. All that's changing is the number of times per year that we're calculating that interest. There is another type of compound interest called continuous compound interest. Continuous compound interest, well, just like it sounds, is compounding the interest continuously. It's not like, 365 times per year. It's not 12 times per year. It's constant. And there's a special formula. There's a very special formula for compounding interest continuously. A equals, it still starts off with our principal, but this time, instead of it being, 1 plus our rate over the number of times per year, all of that simplifies down to E, crazily enough. Now remember, we learned at the beginning of this unit, or I told you guys, that E is actually Euler's number. E is not a variable. It's the number 2.718. So as we increase the number of times we're compounding per year, that this 1 plus the rate over the time, this whole thing gets closer and closer and closer to 2.718. Isn't that crazy? That it just always, no matter what, becomes, if we're compounding continuously, it becomes 2.718, that number. And that's why E is called the natural base, because it appears in nature. And I know you may think, like, oh my gosh, how is finance nature? But it is. This right here is in the natural world. It's not just a random number that we inserted in here. It's actually, like, they solve for E. They realize that as you're compounding nonstop, that base number there is actually 2.718. But anyway, you don't need to know any of that. All you need to know is that when you're compounding interest continuously, your base number is E, and it's still being raised to your rate times time. So when you're trying to remember this or memorize, which you don't have to memorize this year, but if you were trying to memorize this formula, it's always referred to as PERT. P-E-R-T. It spells PERT. You use the PERT formula. So let's try it. Suppose $800 is invested in an account at 6% interest rate, compounded continuously. If no other withdrawals or deposits are made, find the balance of the account after 20 years. So we're going to use PERT because it tells us it's compounded continuously. Our principal is how much in this one? Yes, we're investing $800 into the account. E is not a variable. Remember, it's actually a number, just like pi is a number, so we're just going to write down E. What is our rate? What is our rate? Yes, we take that decimal that's after the 6 and move it to the left. It becomes 0.06 is our rate. And lastly, what's our time? $20 years. Very good. So I just take this and I plug it in, 800 times E. You can get E by hitting second ln. Nope, I didn't click the second. Second, oh God. Second ln. There we go. 0.06 times 20. And you get 2656.09. Now this isn't drastically bigger. It's not crazily bigger than, say, if you were compounding monthly, 12 times a year. I think it's, I did it last class. I think it's like, I don't know, $14 more. But still, $14 is a lot of money. If you keep investing money into this and it's compounding continuously, you're going to make a lot of money off of your money in the end. Okay, so let's see. Do I want to do number 7? No, it's too easy. Let's see. Let's do 8, and then we'll be done. Number 8 says Carla is investing $1,500 in a new 30-year retirement account. Okay, so this is for retirement. Determine which of the interest rates and compounding periods shown to the left would be her best investment option. So She's shopping around. She's trying to figure out, okay, where should I invest my money so that I can retire with a good amount of money? And option A tells her that it's 5.5% annual interest compounded monthly. So it's compounded 12 times a year. So our N for this first option A is 12. And for option B, it says 2.7% annual interest compounded continuously. So remember, you may be thinking right off the bat, okay, compounded continuously is good. That's great. But both of these options have different rates. We need to figure out, is this rate for option A good enough to make it better than compounding continuously with a 2.7 rate? We need to figure out which one is going to make us more money, because Carla wants to retire with a lot of money, like we all do. So I'm going to, on option A, be using my normal compound interest formula, not the continuously compound interest formula, the PERT formula. Instead, we're using the A equals the initial amount times 1 plus the rate, which in this case, I move the decimal place 2 to the left, and it becomes 0.055 over my N, which we already determined was 12, raised to 12 times. Now this is a 30-year retirement account, so I want to know how much money I'll have in 30 years. So we're doing this to see what she should be investing her money in. This is not going to determine, oh, I know I'll have this amount in 30 years, because with retirement accounts, you're putting money in every single paycheck. This is just her trying to decide, okay, which one is she going to use? So we have 1,500 times 1 plus 0.055 divided by 12 raised to the power of 12 times 30. Okay, so this looks pretty good, She is taking her money, and let's see how many times larger that is, just because I'm curious. And she is multiplying it by 5 in 30 years. That's pretty decent. That's you earning money for nothing, right? That's smart of her to put it in this account. But let's see what option B gives us. Now this is compound continuously, so we need to use that PERT formula. A is equal to the principal, which again is 1,500, times E raised to the power of the rate, which again is, well, no, not again. This is a different rate. We move the decimal place 2 points over, and we get 0.027 times time, which is again 30. Whoops, too many zeros. No, oh my gosh. Times E, 0.027 times 30. Okay, so clearly here option A is better. If she was to invest in the second account, she would only be doubling, a little over doubling her money, which is still good. I mean, that's still decent. But obviously, multiplying by 5 is where she should put her money. That's what's going to make her retire with the most amount. I don't know if that's realistic, to be honest with you. Because, most people with each paycheck, put into a retirement account between $100 and $500 per paycheck. That's normally 2 times a month. So that's let's see. That's $6,000 a year she's putting in. Whoops, no. Yeah, actually, that might be realistic. And then you accumulate interest on that. Maybe. All right. Sorry, I went off on a tangent there. But option A is clearly better for her. Are there any questions on finance?